In 2023, the Ford F-Series sold more than 750,000 units in the United States. That made it the best-selling vehicle line in America again. Not SUV, not sedan, a pickup truck. Full-size pickups account for roughly 1 out of every 5 new vehicles sold in the country. The average transaction price now sits between $55,000 and $65,000. Some trims climb past $80,000. This is not a niche market. This is the financial backbone of Detroit. For companies like General Motors and Stellantis, full-size trucks generate the highest margins in their entire portfolio. Industry analysts estimate profit per truck can range from $10,000 to $15,000, sometimes more on higher trims. When you multiply that by hundreds of thousands of units a year, you are looking at billions in operating profit. These trucks fund research. They stabilize quarterly earnings. They keep shareholders calm. So here is the uncomfortable question. If modern pickups are more expensive, more advanced, and more profitable than ever, why are more owners reporting turbo failures, transmission replacements, and major engine work before reaching 200,000 miles? A generation ago, crossing that number was common. Sometimes unremarkable. Something changed. And when this much money is involved, changes rarely happen by accident. At first glance, it feels like you have choices. Ford, General Motors, Stellantis. Different badges, different grills, different commercials promising toughness and legacy. But when you zoom out, the full-size pickup market in America is largely controlled by those 3 corporations. Nearly every major truck on the road comes from one of them. The competition looks wide. The control is concentrated. Even beneath the surface, the lines begin to blur. Ford and General Motors jointly developed a 10-speed automatic transmission that now sits in multiple truck models across both brands. Different logos, same core engineering, similar calibration strategies built around fuel economy targets. Across the board, the trends are almost identical. Smaller displacement engines replacing larger ones. Turbochargers becoming standard instead of optional. Direct fuel injection systems operating at extremely high pressure. Transmissions with 8, 9, even 10 gears designed to keep engines in narrow efficiency bands. You might believe you are choosing between 3 completely different philosophies of durability. In reality, you are often choosing between 3 variations of the same regulatory puzzle. Because when every manufacturer is chasing the same fuel economy standards, the same emissions limits, and the same quarterly profit expectations, engineering diversity narrows. And when engineering narrows, the trade-offs start to look very similar. To understand what changed, you have to remember what came before. If you grew up around trucks in the 1990s or early 2000s, you probably remember engines that felt almost agricultural in their simplicity. Large displacement V8s, 5.0 liters, 5.7, even 7.4 liters in heavy-duty models. They were not subtle, they were not efficient, but they were rarely working near their limits. Most of them were naturally aspirated. No turbochargers compressing air and raising cylinder pressure far beyond atmospheric levels. Lower peak pressures meant lower mechanical stress on pistons, rods, and bearings. Lower exhaust temperatures meant less thermal strain on valves and manifolds. These engines made their power through size, not boost. Fuel delivery was usually port fuel injection. Gasoline mixed with air before entering the combustion chamber, and that fuel passed over the intake valves every cycle. That simple detail helped reduce carbon buildup. Intake valve cleaning was not a routine maintenance item. Transmissions were simpler too. 4-speed automatics were common. Some trucks moved to 5 speeds. Fewer gears meant fewer clutch packs, fewer shift events, and less software managing every ratio change. When they did fail, rebuilds were expensive but mechanically straightforward. Independent transmission shops handled them every day. Many of these engines were also conservatively tuned. Thick cast iron blocks, generous oil capacity, timing chains designed for long service intervals, power outputs that left room in the design. Engineers often built in margin because fuel prices were low and emissions rules were less restrictive. As a result, seeing 200,000 or even 300,000 miles on a work truck was not rare. Construction fleets, rural contractors, even municipal service vehicles regularly crossed those numbers. Reaching 200,000 miles did not feel like beating the odds. It felt normal. Those trucks burned more fuel, they produced more emissions, they lacked refinement, but they were engineered in a different environment. And that environment shaped how long they were expected to last. The shift did not happen overnight. It happened piece by piece. One of the biggest changes was downsizing. A 5.4-liter naturally aspirated V8 gave way to a 3.5-liter V6 with twin turbochargers. On paper, the smaller engine produced equal or greater horsepower and torque. In practice, it achieved that power by increasing cylinder pressure dramatically. A turbocharger can spin at 150,000 to 200,000 revolutions per minute. Exhaust gas temperatures feeding the turbine can exceed 900 degrees Celsius under load. That means more heat, more pressure, and more complexity packed into a smaller physical space. The engine is doing more work per cubic inch than ever before. At the same time, direct fuel injection became standard. Instead of spraying fuel into the intake port, gasoline is injected directly into the combustion chamber at extremely high pressure. This improves efficiency and power control. But because fuel no longer washes over the intake valves, carbon deposits can accumulate over time. Many owners now face intake valve cleaning procedures, sometimes called walnut blasting, costing several $100s. Cylinder deactivation systems were added to improve fuel economy. Under light load, the engine shuts down half of its cylinders to save fuel. In theory, it is seamless. In reality, it adds lifters, solenoids, and oil control pathways that must function perfectly. When they do not, repairs can be costly. Transmissions evolved even faster. 6 speeds became 8. 8 became 10. More gears allow the engine to stay in a narrow efficiency band, improving official fuel economy ratings. But they also introduce more clutch packs, more hydraulic circuits, and more software calibration. A modern full-size truck transmission replacement can range from $6,000 to $10,000. Start-stop systems add additional ignition cycles in daily driving. Aluminum components replace heavier iron to reduce weight and meet fuel targets. Electronic control units manage boost pressure, ignition timing, air-fuel ratios, and transmission behavior in real time. None of these technologies are inherently flawed. In fact, they are impressive. But together, they create a drivetrain that operates closer to its mechanical limits than the trucks that came before. These engineering changes did not emerge in isolation. They were shaped by regulation. In the United States, fuel economy is governed by corporate average fuel economy standards, commonly known as CAFE. First introduced in the 1970s after the oil crisis, the rules have tightened significantly since the mid-2000s. Automakers must meet a fleet-wide average miles per gallon target across the vehicles they sell each year. If they miss that target, they face financial penalties. In recent years, fines have reached into the hundreds of millions of dollars for large manufacturers that failed to meet required averages. That creates a powerful incentive. Every tenth of a mile per gallon matters. At the same time, emissions standards for carbon dioxide and other pollutants have become more restrictive. To comply, manufacturers reduce engine displacement, add turbocharging, refine combustion timing, and increase the number of transmission gears to keep engines operating at peak efficiency. On paper, the result is impressive. Modern trucks produce far more power than their predecessors while achieving better fuel economy ratings. But there is another quiet number that shapes engineering decisions. Most powertrain warranties last 5 years or 60,000 miles. Some extend slightly further, but that window defines the manufacturer's legal responsibility. Components must reliably survive that period under normal use. Beyond that, durability becomes a balance between reputation, cost, and competitive pressure. Modern engines are not necessarily designed to fail early, but they are engineered within constraints that prioritize efficiency targets and warranty coverage first. Long-term durability, beyond 200,000 miles, is no longer the primary design benchmark it once was. When you step back, 3 forces begin to overlap. The first is regulatory pressure. Fuel economy targets and emissions limits push engineers towards smaller engines, higher compression ratios, turbocharging, and tightly managed combustion cycles. Every gain in efficiency often comes from extracting more work out of less displacement. That means higher internal pressures, higher temperatures, and narrower operating margins. The engine becomes a precision instrument, optimized to meet a number. The second force is financial structure. The modern truck market runs on financing and leasing. Many buyers trade in their vehicles within 3 to 5 years. From a corporate perspective, durability beyond that window does not drive new sales at the same rate as technology, towing capacity, or interior upgrades. Revenue also extends beyond the initial purchase. Dealership service departments, replacement parts, and extended warranties form a significant portion of long-term profit. The truck is no longer just a machine. It is part of a revenue ecosystem. Mate. The third force is cost optimization at scale. Global supply chains, shared platforms, and common transmissions reduce manufacturing expense. When Ford and General Motors co-develop a 10-speed automatic, it spreads research and development costs across millions of units. When aluminum replaces iron in key components, weight drops and fuel economy improves. But lighter materials and tighter tolerances also demand more precise maintenance and operation. Individually, each force makes sense. Regulators want lower emissions. Corporations want stable returns. Engineers want efficiency gains. But when all three converge, priorities shift. The truck is engineered to meet regulatory targets. It is engineered to satisfy warranty obligations. It is engineered to remain competitive in quarterly earnings reports. Longevity beyond 200,000 miles becomes a secondary outcome rather than a primary goal. Not because anyone openly decided trucks should not last, but because the system rewards efficiency, compliance, and cost control more directly than it rewards mechanical excess. And systems shape machines. So what can you do if you plan to keep a truck for the long haul? First, consider engine design. If a naturally aspirated option is available, it may operate under lower long-term stress than a smaller turbocharged alternative. Fewer forced induction components mean fewer high-speed bearings and heat cycles to manage over 150,000 miles. Second, adjust your maintenance strategy. Many modern transmissions are described as sealed for life. In practice, fluid degradation still occurs. Proactive transmission fluid changes, even if not strictly required in the owner's manual, can extend service life. The same applies to engine oil intervals, cooling systems, and carbon cleaning for direct injection engines. Third, calculate total ownership cost. Replacing a turbocharger can cost $3,000 to $5,000. A full transmission replacement may range from $6,000 to $10,000. If improved fuel efficiency saves 1 mile per gallon over 100,000 miles, the fuel savings may not fully offset a major drivetrain repair. The key is not fear. It is awareness. When you understand how the system is built, you can decide how long you expect your truck to serve you. So what changed? Fuel economy regulations tightened. Corporate profit models evolved. Engineering priorities shifted toward efficiency and compliance over mechanical excess. Those three forces converged, and the modern pickup was shaped inside that system. Today's trucks deliver more horsepower, more torque, and better fuel economy than ever before. But they are optimized for emissions targets, warranty windows, and quarterly earnings. If you expect 200,000 miles, you cannot assume durability is automatic. You have to choose carefully, maintain deliberately, think beyond the monthly payment. If this breakdown helped you see trucks differently, subscribe for deeper investigations into how modern machines are really built. Because understanding the system is the first step to making it work for you.